Hello everyone, I am Alberto Basaglia, a postdoctoral scholar at the University G. D'Annunzio of Chieti Pescara, Italy, and I'm happy to present at the 2021 SAHC conference our most recent work on assessing the impact of seismic risk mitigation at the urban scale on community resilience and housing recovery. Before I start, I would like to thank my co-authors, Professor Alessandra Aprile from the University of Ferrara, Professor Enrico Spaccone from my same university, and Professor Luca Pelà from the Universitat Tecnica de Catalunya, Spain. In my presentation, I will cover the motivation of our work, as well as the adopted methodology and obtained results. Then I will discuss main findings and conclude with some suggestions for future works. The motivation of our work stems from the high impact the major seismic events had in Italy in the last decade, starting from the 2009 L'Aquila earthquake, which caused the death of more than 300 people, then moving to the 2012 Northern Italy earthquake, which caused the death of almost 30 people, and finally with the most recent 2016-2017 Central Italy seismic sequence, which caused the death of almost 340 people. Earthquakes are events that may last up to 1 or 2 minutes, but whose consequences may last up to decades. And this is due to the long process of recovery. For this reason, researchers and stakeholders have increasingly put their attention on assessing disaster resilience. That is the ability of a system, in case of a city, to return to its original functionality. And for earthquakes, the functionality may be associated with the functionality of the built environment, so buildings and infrastructures. Yet, the time from the earthquake occurrence to the time of complete recovery may last from months to decades. The long recovery process is mostly due to the time needed to repair or rebuild damaged buildings. And this is oftentimes associated to direct losses, direct economic losses. Yet there are a number of other losses oftentimes overlooked that are referred to as indirect losses. And an example is housing recovery. That is the process of people whose building is damaged to move from a tent in the aftermath of an earthquake to a mobile home and finally to a permanent housing solution. And to investigate housing recovery, we analyze the variation in the number of households living in a mobile home, here called PMAR, or receiving an allowance for alternative housings, here called CAS, for 2 cities affected by the 2012 Northern Italy earthquake. And data was obtained from the 2 cities' town journals. Additionally, we performed a cost-benefit analysis of seismic mitigation strategies at the large scale. The seismic mitigation here is associated with the structural reinforcement of buildings. Data of buildings affected by the 2012 Northern Italy earthquakes in the 2 cities under assessment was extracted from the so-called DADO database that was set up by the Italian Civil Protection Department to collect all forms used in the earthquake aftermath to assess building occupancy. And structural reinforcement was also linked to a recently introduced seismic class, ESV class, that ranges from A plus to F, with A plus being the highest and F being the lowest. And they are each class is associated to a percentage of expected lateral forces that the building is able to withstand. This classification is consistent with the already in use classification for energy efficiency, and it is currently used as a guide for the state-provided tax breaks for seismic retrofit. So, focusing at first on the housing recovery, Here we can see values of PMAR, so people living in mobile homes, and CAS, so people receiving an allowance for Concordia sulla Secchia and Mirandola over a 9-year period, from May 2012, so the earthquake occurrence, to May 2019. And we can see that both Concordia and Mirandola, during 2017, no more households were living in a mobile homes, but still there were households receiving an allowance. We can observe also that data is scattered, as it was not completely provided in the town journals, and also the scale of the two figures is different, and it reflects the difference in the population between the two cities, as Mirandola has almost 4 times the population of Concordia. By interpolating these values, it was possible to derive a continuous variation for PMAR and CAS. And we assumed that the housing recovery was due to the sum of these two values. And here we can see the figures, the curves of housing recovery for Concordia in red and Mirandola in blue in the figure on the left. Then we normalized these curves with respect to the population that we said before it is different. And we observed in the figure on the right that the housing recovery trends for the two cities is similar. For this reason, we decided to interpolate these two curves and find the best fit for an equation that can represent the housing recovery for the two cities. And in this case was found to be an exponential curve, due to its simplicity, so to avoid bias in the interpolation process, and because it is monotonic decreasing. And with this curve, it is possible to predict when the two cities will achieve a complete housing recovery. Moving then to the seismic mitigation at the urban scale, here you can see the damage distribution of a reinforced masonry in blue and reinforced concrete in red buildings for Mirandola and Concordia sulla Secchia. Data was extracted, as said before, from the Dado database, as well as the square meter for each building. And the damage is classified according to the European microseismic scale, so with 6 damage levels, ranging from D0, no damage, to D5, complete collapse. To include the structural reinforcement, we decided to adopt 5 class upgrades. So we associated a structural reinforcement with an upgrade in the seismic class seen before and a reduction in the expected damage. So for example, the class upgrade 1, all buildings which were classified as E in the classification for seismic class now move to the seismic class D, and this is reflected by a decrease in the expected damage that moves from D5 to D4. And 5 class upgrades have been considered, so to have that all buildings which have undergone collapse in the 2012 and 2023 earthquake may now undergo no damage. And examples of techniques needed to achieve these class upgrades are also listed in the table. We will see some examples in the following figures. And for all class upgrades, we assumed a fixed cost of 300 euros per square meter based on engineering judgment. Then we compared the cost of structural preventive reinforcement with the cost of repair and reconstruction after the earthquake occurrence. And the cost of repair was assumed based on values available in the literature. We can see, for example, 2 techniques to achieve a class upgrade 2. Actually, there's a mistake in the slide. For our reinforced masonry buildings, this upgrade can be achieved using, for example, introducing, for example, bond beams and tie rods that guarantee the box-like behavior for reinforced masonry buildings, or using fiber reinforced polymer wrapping and embed through section technique for reinforced concrete buildings. These 2 techniques increase the shear strength and prevent brittle failure. Then moving to class upgrade 3, in this case, for our reinforced masonry buildings, we can use the wall-to-wall connection with steel frames to make distant walls work together. In the case of an earthquake, or for reinforced concrete building, we can strengthen infill walls to prevent the out-of-plane collapse. So comparing the cost of preventive strengthening and repair costs after the earthquake, we can see that the optimal point given by the intersection of the two curves for both Mirandola and Concordia is found to be between the second and the third class upgrade. So between class C ESV and B ESV in the seismic classification. And so it is associated with an expected resistance to lateral forces of 60%. So discussing main findings, by using the obtained curve for the housing recovery for the two cities, we can predict that the Concordia and Mirandola will achieve a complete housing recovery in 13.5 years. And as of 2021, so over 9 years after the earthquake, recovery is still ongoing. Limitation, of course, of the proposed approach are the scattered data and the absence of information on permanent displacement. Then for the seismic mitigation at the urban scale, we found out that the optimal reinforcement for existing building corresponds to resistance to lateral forces of approximately 60%. This value is consistent with the actual provision of Italian guidelines in the building code for the strengthening of existing building. The limitation of this approach is the empirical method of deriving the damage and the fixed cost for the class upgrade. So in conclusion, disasters such as major earthquakes have impacts on communities that may last up to several years. And these long-lasting effects greatly contribute to the final sum of economic losses. And this is without considering other implications that disasters have on communities. So preventive seismic mitigation is crucial, is the only way to actually reduce losses and achieve a faster recovery. And future works will aim to validate obtained findings in order to have a more complete understanding of housing recovery and recovery in general. Here you can see listed the main references used in this work. And if you want to know additional details, I encourage you to read our publication on the Bulletin of Earthquake Engineering. And with that, I thank you for your attention. If you have any comment or question, please reach out via email. And with that, thank you again for your attention and enjoy the rest of the conference.